Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to Chibui Secondary School e-learning platform. Your presenter is Mr. Chitamwe Rashid. Continuing with our study of current electricity. I need to register our apologies for what happened last time. We started when the notes are not there, but we are very sure today the updated notes are already there, so you look at it as we try to follow and then we move along. Previously we talked about Ohm's law, and we stated it by saying that the current flowing through a conductor is directly proportional to the potential difference across the ends of the conductor, provided temperature and other physical conditions remain constant. We said once those physical conditions change, then Ohm's law will not be valid. And the statement of Ohm's law is summarized in this equation: V is equal to I R, where V is the potential difference, R is the resistance of the conductor, and then I is the current flowing. Previously we had said when you talk about potential difference, we want to make an imagination that we have a fall of water at a given height, h, and then another height, h2. Water is flowing like this from a high potential to a low potential. And now we assume that now the water is now the current, and the height difference is a measure of the difference in potential energy, and this is the potential difference. And therefore the speed with which the water is moving depends on the difference in the heights. So therefore even current flow depends on the difference in the potential. The difference in the potential between the highest point and the lowest point determines the rate of flow of charge, and therefore rate of flow of current. Therefore, as the potential difference is increasing, even the current is increasing. Meaning that as the height difference is increasing, even the speed with which the water is moving has to increase. And that's why we are saying that the PD across the ends of the conductor is directly proportional to the potential difference across. Now how about resistance here? Resistance here may depend on a couple of factors. One, how wide or thin the tube with which water flowing is. Meaning that if the tube is thin, it implies the speed with which water is spouting out is going to also increase. And if the pipe is large, it implies that the pressure is going to be low. And therefore this resistance may be depending on a couple of factors like cross-sectional area, that is thinness or wideness of the wire or conductor for that matter. Or it may also depend on the length, how long the tube is. It may also determine the resistance factor. So therefore, our concern today, we want to talk about resistance and resistor. Resistance and resistor. Now what do we call a resistor, or resistance for that matter? So we are saying a resistor or resistance is the opposition to the flow of current. The opposition to the flow of current. SI unit is ohm. SI unit is the ohm. Ohm is O, ohm. Symbol, that is the symbol. Definition of an ohm. You see, from this formula, V is equal to IR. Resistance is now going to be now V over I. It implies that for a resistance of 1 ohm is equal to 1 volt over 1 ampere. Therefore, in our definition, we are going to say that an ohm is the resistance of a conductor which allows the current of 1 ampere to flow through it when the potential difference across the ends of the conductor is 1 volt. Current flowing of 1 ampere when the PD is 1 volt will correspond to a resistance of 1 ohm. How about a resistor? A resistor is a conductor which opposes the flow of current. Now, in our circuit arrangement, we can arrange the resistors in 2 ways. We can either arrange them in series or we can arrange them in parallel. When we arrange them in series, we connect them end to end. End to end. Meaning that you allow current to be flowing, you connect resistor 1 to the extreme end resistor 2, resistor 3, and current flowing is I, R1, R2, and R3. Now the fact that current the resistors are in series, the current flow is the same. Current flowing through the resistor is the same. Current is the same. Now, when current passes through resistor R1, we create a potential difference across R1, and that is V1. Same applies to 2V2, same applies to 3V3. A PD across each ends of the conductor. Now from Ohm's law, V is equal to, from this one, you can see the total voltage is going to be equal to V1 plus V2 plus V3. Now, from Ohm's law, V is equal to IR. V1 is going to be equal to IR1. V2 is going to be equal to IR2. And V3 is going to IR3. Now, since current is the same, we can factorize it out and say IR is equal to I into R1 plus R2 plus R3. Then these i's can cancel. If you divide I on either side, the i's do cancel out. And then we get the resultant resistance to be R1 plus R2 plus R3. So, if resistors are connected in series, the resultant resistance, sometimes we call it the effective resistance, is the sum of the individual resistances. Meaning, the effective resistance is greater than the greatest resistance. So that's what we covered last time, but I'm making a review due to some disruption that happened in our previous lesson. So I'm making a review slightly backwards in order to conceptualize the thing. Now, if resistors are connected in parallel, once they are connected in parallel, it implies that if we have resistor R1 and resistor R2 and resistor R3, the three of these resistors are having a common point. A common point. That means if you connect a voltmeter here, the PD you are going to register here is the same PD across R1, same PD across R2, same PD across R3, because usually the PD is obtained across the ends of the conductor. And the end of the conductor is common to the three. Therefore, the PD across here is the PD across each of these ones. So, if we allow current to come here, once it reaches this junction, it is going to subdivide into I1, I2, and I3 across individual resistances. So now, it can recombine and then continue. Recombine to form I again. Now, we say in parallel, PD is the same because they have common intersection. So since PD is the same, but current is different, we are going to say that in parallel, PD is the same. Current is shared, current is divided. Current is shared or divided. If current is divided, it implies therefore I is equal to I1 plus I2 plus I3. Now we apply Ohm's law. Ohm's law, V is equal to IR. It implies that I is equal to V over R. So where there is I here, we are going to place V over R is equal to V over R1, since V is the same, V over R2 plus V over R3. So, since PD is the same, what we are going to do, we factorize out the V. Once we factorize out the V, we are going to come up with V equal to I V over R. The V is common, we bring it up, we factorize it out. Inside we remain with 1 over R1 plus 1 over R2 plus 1 over R3. Now we can divide both sides by V. That one will imply that the V will cancel. And so we remain with 1 over R equal to 1 over R1 plus 1 over R2 plus 1 over R3. So this expression here turns out to be the effective resistance in parallel, or the resultant resistance when resistors are arranged in parallel of that nature. But we are saying there is a special case for two resistors. For two resistors, in parallel. For two resistors in parallel, we are realizing that 1 over R is equal to 1 over R1 plus 1 over R2. We get LCM, R1 plus R2 R1, R2. This one divide by that, we get R2. The whole of this divide by that, we get R1. So, if 1 over R1, R is equal to R2 plus R1, it implies that if we make the inverse and make it R over 1, 1 over R, R over 1, meaning that what was the denominator turns out to be the numerator, and the numerator turns out to be the denominator. So addition is having no problem with interchanging. Whether it was R2, R1 is the same as R1 plus what? R2. There is no serious problem with that. So therefore, the R down is meaningless, and therefore the same as R. And if it's the same as R, therefore effective resistance for two resistors is going to be called the product of the resistances divided by the sum of the resistances. Product of the resistances divided by the sum of the resistances. So in other words, whenever you are given a circuit that is having only two resistors, you may not bother yourself with the whole of this. You can just use product over sum and then you evaluate. So we can now do some examples. We did them the other time, but I think it may not cause any harm if we make a simple recap, a few examples of what we did previously. So we said, example 1, we are having two resistors in series. I think that one is obvious. We just add. If they are resistors in parallel, we use product over sum. For example, part B of the question, which was having two resistors in parallel. Like this. In parallel, common, the current subdivides like that. And therefore this was 2 ohm, this was 4 ohm. So how do we get the effective resistance? We will not bother ourselves much. We are simply saying effective resistance R is going to be product of the resistances divided by the sum of the resistances. And that one is going to give 8 divided by 6 and gives an answer of, that is 4/3. That is 1.33 ohm. As short as that. Now what if we had part C? What if it is like this, and then we are having resistors of this kind. R here is given as 2 ohm, and then this is also 2 ohm and 4 ohm. You realize now 2 ohm, 4 ohm is the same as this one. We only adding this one. So what we do, we first get the one in parallel. The one in parallel is going to be in series with this one. So in this case, what we will do, we will say effective resistance R in summary, product over sum. The whole of this is now in series with this, so we shall add just plus 2. Already this one is 1.33. If you add 2, that is going to be equal to 3.33 ohm. Short and simple, like that. Then, number 2, we had the figure shows a network of resistors. Calculate the effective resistance. So we had a figure we had a figure. It was arranged like this. Look at it. So I have a point there and another point there. This is P, this is Q. The resistance here is 2. Here the resistance is 3. Resistance is 5. Now the question is asking, calculate the effective resistance between points P and Q. So, the resistance P and Q is actually the effective resistance in that combination. So what we are going to do, we get the one in series. The resultant of series is going to be effective with the parallel. So effective resistance, I'm going to use the shortcut method. It's going to be, I deal with series first, 2 plus 3 product is times 5 over sum, which is 2 plus 3 plus 5. Have you understood that one? Yeah?
But why did we just add the other side? But here we are multiplying and adding.
Someone is asking, why did you multiply this other side? You said these ones are in parallel. Product, this one is 4. So product over sum. That one will cater for the parallel. Now the resultant of parallel is now in series with the 2. You're getting it? So that's why we say product over sum plus 2. We get 3.3. Now this time round, these ones are in series. You first get the resultant of the series, which is 2 plus 3. Now 2 plus 3 is in parallel with the 5. So product is going to be the resultant of the series that is multiplied with the 5, and then sum, the result of the series, we add it with the 5. You now get it. I'm just making a summary. I'm not writing a lot. Otherwise, what we may have done, we may have first of all said 2 plus 3 we get 5. Then we say 5 times 5 over 5 plus 5. Are you getting it? It's the same thing, only that we wanted to summarize it. So in this case, 5 times 5 is 25. And then 5 plus 5 is 10. And the answer is 2.5 ohms. 2.5 ohms. Number 3. The effective resistance of two resistors of resistance 5 and 15 joined in series and then placed in parallel with the 20. Number 3. Effective resistance of two resistors 5 and what? 15 were originally in series. So we can arrange it. It was originally in series, 5 ohm, 15 ohm. Joined in series and then placed in parallel with the 20. Placed in parallel with the 20. Do you see any difference between the previous number and this number? Do you see a big difference between this number and this number? They're the same. Okay, the values are different, but the structure of the question is the same. Only that this time around they gave you in words. They did not give you in a diagram. So you interpret and make your own diagram, and then you substitute. So this time around, let me make a simpler one. In series, I'm just changing the approach bit. In series, 5 R1, let me call it R1 is equal to 5 plus 15, giving 20. So, new diagram is now going to be 20. This one now is 20 over another 20. It is the same approach, only that this one gets the same marks and this one gets the same, only that this one is more simplified. So I've now redrawn the diagram after catering for the series. Have you noted that one?
Yes.
So now I've now simplified this diagram to a new diagram. So now there are two resistors in parallel. So now final resistance is product over sum, which is now going to be 20 by 20 over 20 plus 20. And the answer turns out to be 400 over 40. So the answer is 10. So that is 10 ohms. Hoping by now getting effective resistance is not a serious challenge. Now, an activity was given. I think that's where our lesson today begins. We are given a battery is rated 90 ampere hours. Suggest the meaning of 90 ampere hours. Part B. Calculate the time for this battery in A above to supply current of 3 amperes. Question 2. Classify the following materials as electrical conductors or insulators. Aluminium, foil, air, copper, rod, plastic, nail, wood, copper clip, and glass. Then calculate the effective resistance between X and Y. I hope you tried these questions out. And this, compare your answers with the following that I worked out. Down. Part A. 90 ampere hour means the quantity of charge delivered when a battery supplies current for 1 hour is 90 coulombs. The quantity of charge delivered when the battery supplies current for 1 hour is 90 coulombs. Is 90 coulombs. I'm saying 90 ampere hour means the quantity of charge delivered when the battery supplies current for 1 hour. For 1 hour. That quantity of charge is 90 coulombs. That is what we mean by ampere hour. Someone is asking, that in finding resistance, is the method apply for only 2 resistors or even 1 resistor? You need to know, if it is 1 resistor, there is no need to finding effective resistance because it is the only resistance that is available. Are you getting it? For 2 resistors, that is the shortcut method. But we can also use the other original method of 1 over R1 plus 1 over R2. It can also work. But this method cannot work for 3 resistors and more. It is only for 2 resistors. Thank you, Narima Husna, for that clarification and response. Thank you so much. Others, you can also send your grievances and queries or additions and subtraction if you feel you are not contented by the approach. Thank you so much. All right. So, part B, quantity of charge is given by IT. And our interest here, and this time round is time. We make T the subject of the formula. T is now going to be Q over I. According to our question, the charge was given to be 90, and the time and the current were 3 amperes. So therefore this was 30 hours. And why maintaining hours is because the 90 was ampere hour. So if it was ampere hour, so we are going to maintain it to be hours. Alright. Then we are told to classify conductors and insulators. You are going to look at the table we put. You could see conductors, we have aluminium foil, copper rod, nail, clip. Insulators, you have air, plastic, wood, and others. Hope that you also tried it out that way. Then, about the calculation, the answer for part B was supposed to be 9.5 using the approach we have tried. Then, question 3, Ohm's law, we said, states that the current flowing through a conductor is directly proportional to the potential difference across the ends of the conductor, provided temperature and other physical conditions are kept constant. Non-ohmic conductors include tungsten filament, thermionic diode, neon gas, semiconductor diode, dilute sulfuric acid, and others, as we had previously covered in the other lesson. Then we are told to come up with an expression for effective resistance in parallel for 2 resistors. I said, like the way we have derived from the beginning of the lesson, here you don't begin in the middle. You trace it from where we had started. So he said for 2 resistors in parallel, it is going to be arranged like this. So when resistors are arranged in parallel, the PD is the same, assuming this is R1 and this one is R2. The current is divided into I1 and I2. So the first points that you get are 2. One is that PD is the same, PDV is the same. That is already half mark. Then you can now say current is shared. Current is shared. And what do you mean by shared? We are saying that the total current is equal to the sum of the individual current. The current entering this place, the junction, is going to equal the sum of current leaving the junction. So total current is the same sum of the individual currents. So we are now going to say I equal to I1 plus I2. It's just common sense. Current coming divides. That means the subdivisions are equal to the total current. Then from Ohm's law, we substitute V over I, R. This is V over R1 plus V over R2. Factorize out, V over R is equal to V into 1 over R1 plus 1 over R2. So the V's cancel, we remain with 1 over R equal to 1 over R1 plus 1 over R2. Get the LCM, R1, R2. Divide this one by that, you get R2. Divide this one by this one, you get R1. So that one implies that R over 1 is the same as R1, R2 over R1 plus R2. So our thing is product over sum.
Teacher,
Yes?
I made a mistake.
Wait.
Because you said that
R2 over R1.
yeah,
R2 over R1 is the same as
R2 plus R1, then out of R1, R2. Then here you said R1 out of R1 plus R2. Like the product, the other on the other first LCMs.
you see 2 plus 1 is the same as 1 plus 2. Yes? There's no major difference. Are you getting it? 2 plus 1 is 3 and 1 plus 2 is 3. Is there a problem? Here, this was 1 over R, this is R. Are you getting it? It has been inverted upside down. So that's for 2 resistors only. It does not work for more than 2. Now, part C of the question was related to this diagram. So the circuit was arranged like the way you see it there in your notes. We have a short terminal and a long terminal. A long terminal like this, meaning that this one is negative terminal and the long one is a positive terminal of the battery. So this resistor is 2 ohm. This one is 8 ohm. This is 6 ohm. And then this one is 3 ohm. So that is the circuit arrangement. Now, our interest first of all to get the effective resistance. So what we will do, we'll deal with the parallel arrangement first. We use, because there are 2 resistors, so we'll use product over sum. Then the series, we just add them on. So therefore, effective resistance, effective means resultant, R is going to be equal to product over sum. This is the parallel arrangement, you have resolved it, plus 8 plus 2. So this one finally gives the answer to be 12 ohms. So the effective resistance here is 12 ohms. Now we have to get the PD across the 8. PD across the 8. Now, already the current was given to be 1.5 volts, 1.5 amperes. Here we just use Ohm's law. So, Ohm's law, V is equal to I, R, the current is 1.5, the resistance is 8. And therefore, the PD across is 12 volts from Ohm's law. Then the EMF of a cell. EMF, in other words, the supply EMF. Remember how we defined EMF. We said EMF is the total work done to move one coulomb of a charge around a complete circuit in which the cell is connected. So that one means there is a driving force that drives the charge or drives the current throughout the circuit. Now you are going to realize that the EMF is actually the total PD, because PD is only driving current through 2 points in a circuit. Now EMF is driving current through all points in the circuit. So that one implies that EMF of the cell is the total PD of the circuit. EMF E is equal to total PD. in the circuit. In the circuit. And if that's true, so that means to get EMF, we get total current times total resistance. You get the total PD of the circuit. So therefore, EMF E is equal to IR, total current times total resistance. And then total current was told to be 1.5, and total resistance we have was 12. And therefore, the total EMF of the circuit is 18 volts. In other words, out of the 18, the 8 ohm consumed 12. And that means the remainder shared the remaining 6 volts. So that is the assignment for the previous lesson. What do you want to talk about today? Factors affecting resistance of a conductor. The factors are 3. And these 3 factors, the first one was talked about in the definition of Ohm's law. We said Ohm's law states that the current flowing through a given conductor is directly proportional to the potential difference across the ends of the conductor, provided temperature and other physical conditions remain constant. Now we are hearing the word temperature, meaning that temperature is affecting the relationship between V and I, and the relationship V and I, the constant is R, meaning that temperature affects resistance. So therefore, how does temperature affect resistance? Now, you are going to refer to a conductor. And this conductor here, you see, is having atoms. So once you connect it to the battery, once you connect it to the what? To the battery, you allow charge to flow, or electrons. So once these atoms vibrate, these atoms, the vibration of these atoms reduce the mean free path for the electrons, where the electrons have to pass in order for current to pass. And you know that the speed of flow of electron is the current. So if the path, you reduce the speed with which these electrons are moving. And once the speed of electrons is reduced, it implies that current flow is reduced, and therefore resistance has increased. You have resisted current flow. And therefore we are now saying that the resistance of a conductor is therefore proportional to temperature. The more temperature increases, the more vibration increases, the more paths are blocked for electron to move, the speed of electrons are reduced, and therefore resistance has increased. Then the second factor is length of the conductor. Now if we keep other factors of temperature and cross-sectional area constant, and then we increase the length of the conductor, we are saying the longer the path for the electrons, the more collisions with the ions of the conductor. Meaning that if the conductor is very long, it implies that these moving electrons are going to meet more atoms along the way, reducing the speed with which they are moving. And once the speed with which they are moving reduces, it implies that the current reduces, and therefore resistance increases. Therefore resistance is proportional to length. The more the length, the more collisions, and therefore the speed is lowered, and that implies current reduces, therefore resistance increases. The last one, cross-sectional area of the conductor. Now we can compare an area of the conductor of this kind and the area of the conductor of this kind. Now, that means that thicker conductors have more number of electrons crossing per second than thinner conductor. Here there are going to be more electrons moving, passing a bigger area. Whereas here I have less electrons moving. And therefore that means here more current, because the rate of flow of electrons is the current, and here less current. And that means current is resisted most in thin wires than in thick wires. Therefore, resistance is inversely proportional to area. The bigger the area, the smaller the resistance, and the smaller the area, the bigger the resistance. Okay, those are the major three factors. But there is something which we need to talk about concerned with temperature. And that is a question. Why a thin wire carrying current becomes hot? You have ever connected a dry cell with a wire, and then once you touch it, you realize it is hot. And that question came in a certain year in your name. I don't recall the year. And that is the question he was asking. Why a thin wire carrying current becomes hot? The idea is connected with what we have already talked about. So we said, when current flows in a wire, the conduction electrons gain kinetic energy from the applied field. As they drift along the wire, they collide with metal atoms and lose some of their kinetic energy to the atoms. The atoms vibrate with increased amplitude, colliding with one another, leading to an increase in temperature. Hence the wire becomes hot. What do I mean? I mean, when you get a wire, we are talking about thin wire. Thin wire, we expect them to have greater resistance. So we are saying when you connect this wire to the battery, the electric field supplies electrons, the conduction energy, with high energy. High kinetic what? Kinetic energy. The kinetic energy of these electrons collide with atoms of the conductor. And in the process of collision, they give out some of the kinetic energy to the metal atoms. So these metal atoms start vibrating to and fro. In the course of vibration, they collide with one another, causing friction amongst themselves, and that means there is an increase in temperature, and therefore the wire becomes what? Hot. Our major concern today is calculation of voltage, and that is going to be the conclusion of today's lesson. Calculation of voltage. In calculating voltage, we employ Ohm's law. Employ Ohm's law. Only a formula of only 3 letters. V equal to I R. That's what we are going to apply. And the first example here, if you have a current of 3 amperes passing through a resistor of 4 2 and 3 ohms, as you see in the diagram. The resistors are in series. The current is 3 amperes, and we are having 4, 3, and 2, and 3. No, the order may not matter that much. So we have to calculate the PD across each resistor. We said when current passes the resistor, there is a potential difference developed. So we are going to use V equal to I R. So therefore, PD across the first resistor, we'll call it V1. PD across the second one, we'll call it V2. And PD across the third one, we'll call it V3. When we apply Ohm's law, V is equal to IR. For V1, is going to be equal to I, which is 3, resistance is 4. So that one gives 12 volts. V2, I is 3, resistance is 2. This one gives 6 volts. V3, I is equal to 3, resistance is 3, and that one gives 9 volts. And that is the answer, short and precise. And then if you are told to hence calculate the total PD, you simply add up the individual PDs. Total PD is equal to V1 plus V2 plus V3. So that is going to be 12 plus 6 plus 9. And then you get the total PD to be, what is the sum? 27. So you get 27 what? Volts. So that's number 1 is over. We can proceed to number 2. Members, if you are not following, you register your concern. You will be getting the feedback, and then you react to it immediately. Number 2, we have a battery of 3 volts. It does not have any internal resistance. That is an assumption. And then the circuit is arranged as it appears in the diagram. So I have a cell. There are 2 dry cells. This is the the negative terminal. Positive terminal, negative terminal of the battery. The total EMF is 3 volts, implying that each cell is 1.5 volts. And there is a resistance here. And here is a parallel setting. And then back to the source. This is 2 ohm. This is 2 ohm. This is 5 ohm. And the question is saying, calculate the effective resistance. I think that one we had already done previously. To calculate effective resistance is going to be cheaper for us. First deal with parallel, and then the resultant is going to be in series with a 5. So effective resistance is going to be product over sum, and then this one now is going to be shrinked to a common resistor, which is now going to be in series with the 5. So 2 plus 2 is 4, and then 2 times 2 is also 4. That means 4 over 4 is 1, plus 5 gives the total resistance to be 6 ohms. Then calculate the total current through the circuit. Total current through the circuit. Here we'll employ Ohm's law. V is equal to IR, meaning I is equal to V over R. The total voltage is actually the EMF, which is 3 volts, and the total resistance, you have already got it as 6, so that is going to be 3 out of 6, and the current is going to be 0.5 amperes. 0.5 amperes. 50 and 0.5 is the same thing. It is only that we prefer to write 50 because the instrument that measures current, which you call the ammeter, records to 2 decimal places. So Roman 2, Roman 3, PD across the 5 ohm. PD across the 5 ohm. Still we are going to use Ohm's law. V is equal to IR. Now the current passing through the 5 ohm is actually the total current, because this one is in series with that. So it is going to remain 0.5, and the resistance is 5. So in this case, 0.5 times 5 becomes 2.5 volts, or 2.50, to cater for the decimal places of the instrument that we use, and that's called the voltmeter. Question 3. Question 3, or example 3. Each of the example is having a certain element is bringing in, and I brought it for the purpose. Now here we have a setup like this time round, positive terminal of the cell, meaning that current is going to be flowing in the positive direction. Here we have many cells which you have added in series to have a total EMF of 20 volts. And then here we have an ammeter placed there. We have a resistor of 3 ohms. We have then parallel arrangement here. And then there is a switch. I wonder whether it will be of any help. There's the switch there. And the setup is arranged like that. This is 2 ohm, 2 ohm, 3. Now the question is, find the ammeter reading when switch K is closed. Switch K is what? Closed. When we close, meaning we switch on K. So, the ammeter reading when K is closed. So you cannot find the ammeter reading. Ammeter reading means we are looking for the current flowing. And from our Ohm's law, I is equal to V over R. Meaning that you have to have the total voltage, which you already have, but effective resistance you don't have. So you need to first find the effective resistance. So according to our circuit, when we close this one is going to be in parallel with this. So effective resistance, we now have done effective resistance, we have now experience. So what we do, we summarize it at once. Product over sum, which is now going to be in series with the 3. So 2, this is going to be 4 out of 4 plus 1, mean 1 plus 3, which is 4 ohms. So after getting effective resistance, you can now find current. Current I is equal to V over R. You could see that the current I is the one that passed through the 3, subdivided here, rejoined. Meaning that the supply current is the current passed through the ammeter. So that one is now going to be equal to 20 divided by 4. and therefore the resistance turns out to be, the current turns out to be 5 amperes. So therefore the ammeter reading, what the ammeter will indicate is going to be 5.00. When you talk about ammeter reading, the reading is recorded to 2 decimal places. For current measuring, we can simply say current is 5 amperes in calculation, but if they say ammeter reading, the reading should be recorded to 2 decimal places. So we indicate it with the 2 decimal places. But if you're just calculating current, doesn't matter how many decimal places you are placing. But if it is a reading has to indicate the number of decimal places. Is that one okay?
Yes.
If it is not clear at this moment, you register your concern and then we try as much as possible to ensure that your query is responded to. Then Roman 2, when K is open. When K is open. When K is open, you need to be careful. When K is open, it will mean that current is going to flow like this. It will not flow through the upper resistor because there is no continuous path for current. So it is going to flow in this direction, lower direction, and then continues bypassing the 2 ohm resistor. So that means that the lower 2 ohm resistor is going to be in series with the 3. So effective resistance this time round, R, is going to be equal to 3 plus 2, ignoring the other 2. And the effective resistance this time around now 5 ohms. So if it comes to getting current I is equal to V over R. The V is 20, the R is 5. This time around the current is 4 amperes. So ammeter reading is 4.00 amperes. That's what the ammeter will read. I hope by now, maybe we try the last example. I'll give you the last example before you go to the activity which you will produce next week. The example 4. We are having a battery of EMF 10 volts, negligible internal resistance, connected to the resistors as shown in the diagram. The diagram is here. We draw like this and put dots to imply that there are many cells we are adding, or generally having a battery of 10 volts. And the arrangement is having the following resistances arranged like this. So this is 2.4 ohms, 2.6 ohms, 6 ohms, and then 4 ohms. So the following are the questions. Calculate the effective resistance of the circuit. Finding effective resistance has become now very easy on our side. Very easy on our side. When you have 2 resistors, we deal with product of the sum, the rest we add. So here, what we will do, effective resistance R is going to be deal with the product over sum 4 by 6 over 4 plus 6. Then we have these ones 2.4 and then 2.6. So 2.4 plus 2.6 gives what? 5. Eh?
Yeah.
And then here 4 by 6,
4 by 6.
24.
Yeah.
24 plus 10,
10.
2.4. 24 divided by 10, 2.4. Plus, this is 5. So this one gives 7.4 ohms. That one gives 7.4 ohms. Now, the second part of the question is to calculate the total current supplied by the battery. We use Ohm's law. I is equal to V over R. Since they're asking total current, we'll use total PD, which is EMF, over total resistance. And that one is going to be equal to 10 divided by 7.4. That one gives 1.35 amperes. That is the total current I. Then Roman 3, PD across the resistor in the parallel setting. And this is where you need to pay a lot of attention, because it is unique from the rest of the things that we have been doing. PD across the parallel setting. You are going to realize that we can have two approaches to this part. We can have two approaches. But the obvious one is to get the effective resistance in the parallel setting, which, if you noted, it is actually here, 2.5. Effective resistance in the parallel setting. Is equal to actually product over sum, which is 2.4. You may not repeat that one. And then our interest is to get the PD across the resistor in the parallel setting. You know why I'm saying the resistor in parallel setting? Because the PD is going to be the same. We have the common ending here. So after getting effective resistance, therefore the PD in the parallel setting is going to be called IR. The current I is the supply current that entered. So the current I you had already calculated it as 1.35. So this is now going to be 1.35 times resistance in the parallel setting, which is 2.4. So the final answer turns out to be equal to 3.24. So this is the PD in the parallel setting. PD in the parallel. This setting here. Now the last question, current through the 4 and the 6. Now this current here, once it reaches here, it's subdivided into I1 and then I2. So the question is asking for current in 4 and 6 is actually asking for I1 and I2. Now since we had said that the PD across the 4 is the same PD across the 6, and you have already got it at 3.24, we are going to simply use Ohm's law. So Roman 4, current across the 4 the 4 ohm, which we called I1, is equal to V over R1, which we will call R1, I'm meaning the 4. So the V, it is V prime, not the total voltage, but the PD across the parallel, which is now going to be 3.24 divided by R, which R of our concern is 4. So that one gives the answer to be 0.54 amperes. So the last part, current through the 6. So their PD is the same. The parallel setting PD is the same. So I2 is now going to be V over R2. So the V is 3.24 divided by R2, which is 6. And there the answer, 3.24 divided by 6, we realize you are getting the answer to be 0.8 amperes. Now we need to note that this current I subdivided into I1 and I2, it implies to prove whether your answer is correct or wrong, you add 0.8, add it with 0.54 and see whether you are getting a total current of 1.35. Are you getting what I'm saying? I'm saying to prove your answer, I here subdivided into I1 and I2. I1 you have got it to be this one, and I2 to be this one. Now to prove whether your answer is correct, you go to your I. I you got it to be 1.35. Add this one plus that one and see whether you are getting 1.35. If you are getting the same answer, then you confirm that you are on the right track. Definitely, I know circuit calculations, mastery need practice. If you don't practice, you find challenges. So continue practicing so that you conceptualize it. And that is the reason why I have given the following activity. The activity is having 4 numbers. Number 1 is the simplest. You are given current, you are given the PD, you are finding resistance. That is obvious. Number 2, you are given a circuit, but the PD that we want is only across the 2. We are given PD across the 2, so we are going to find R. Number 3, you are given a circuit, and then you'll be able to find current I1 and I2 as we have tried to do with the other previous number. And number 4. Members, I want you to pick a lot of interest in this topic because you cannot claim that you are going to be an electrical engineer when you don't know the basics of current electricity. And nowadays, this area of current electricity is the one of the courses that are highly competitive and prestigious courses because people are building estates and they need electrical engineer. We will not allow a Kamufu to go and make a wiring of a house, of an estate, because you cannot risk. And therefore, only one estate is enough to make you a millionaire. So, if you pick interest in this topic and practice it more times, the chances of becoming an electrical engineer is higher, and therefore, the chances of earning are also great. I thank you so much for sharing knowledge with me, and we will continue sharing. Please, if you have anywhere you are not following very well, you can contact me via WhatsApp number and even give it out, 0.0701 324525. My names will appear, so will come for clarification. I'll be able to help out, inshallah. Wish you the best of the day. Assalamu alaikum wa rahmatullahi wa barakatuh.